Welcome back to the classroom. My name is Mr. Wong, and we are continuing on Module 5, Inquiry Question 1 about projectile motion. So you would have seen the previous lesson. If not, please check it out first. And we were introducing what projectile motion was. Now, in this part of the lesson, we're going to actually do some calculations. We're going to try and resolve the horizontal and vertical components of projectiles, meaning by we're solving vectors. Now, you would have done this in Module 1 and Module 2. If you're not comfortable with solving vectors, now is the time to look at this video here, or maybe you might want to look at some of the older videos where we did solve for vectors. So a quick summary of what we define as a projectile. So projectile motion refers to a parabolic path an object takes when thrown, launched into the air with no additional power added to it. Okay, so keep that in mind. The vertical motion is accelerated by gravity, and obviously gravity will accelerate the object down. Hence why if you launch an object, it will always fall down at a particular point in time. The horizontal motion is constant, so meaning by it has a constant velocity, because it does not experience an acceleration. And you can see that by these little time frames that we have here. You can see that the horizontal distance traveled, assuming that each frame is the same period of time passed, you can see the distance covered is changing for the y component. However, for the x component, the distance changed after each time period is the same. So that kind of goes back to these two dot points that we have here. Okay, so when it comes to analyzing projectile motion, let's firstly look at the vertical motion, or the y component. There's a couple of things you can look into to help you understand these calculations a bit better. An object thrown upwards will experience acceleration due to gravity. Okay? It will slow down, so as you can see, that's why it sort of curves, begins to plateau, and halt in mid-air. So, at the point when object, so this is for all objects of any vertical motion, once it reaches this particular point, its velocity will equal to 0. The x component, so the velocity of the x component, there's still some kind of arbitrary number that's still going on, but the y component, when it reaches peak height, is 0. Okay? So just make sure you're really clear on that. As it begins to fall down, it is accelerated by gravity. Now, given the fact that we are dealing with vectors, because velocity is a vector, you do need to differentiate which direction is positive, which direction is negative. Okay, I tend to say anything that's going up is positive and anything going down is negative. So up to you which way you want to work, but make it consistent. If we launch an object on a flat surface and the actual distance or where it lands is on the same height as which you launched it, then you can actually work out some really interesting things. So you can actually work out the time it takes for an object to launch to this part here, so the peak height, and then you calculate times the time by 2 to find the total trip time. So t here is the trip to peak height, and t2 here would be the total trip time of our projectile, as you can see in our relationship that we have there. But you won't be able to work it out for these kind of scenarios. So say you launch an object and they fall a bit lower than where you launched it, or maybe it reaches a point that's a bit higher than where you launched it. You can't use the assumption of working out t and then timesing it by 2. So let's look at some equations that we can implement to understand how projectile motion actually works. Okay, so you might have a little spoiler here already with this equation, but regardless, in Year 11 kinematics, you have been introduced to 3 equations. This one here, to explain how the final velocity is changed if the object is accelerating. this one here to see what the final velocity is based on the acceleration and displacement, and this one here, looking at the overall displacement of the object if it traveled at a particular speed initially and then it accelerated over time. So when it comes to year 12, when we look at projectile motion, we need to take into the fact that we're looking at two different sets of motion. We're looking at a motion moving of the y component or the vertical component, and we're also looking at motion in the horizontal component. So this equation here, we can just simply convert it, add some subscripts with a little lowercase y, and this is the new equation we can use to analyze projectile motion in the vertical direction. So that's what you have here. And then with our equation here, we can rewrite that and subscript y here. Now, instead of writing s, I'm just going to write delta y to represent the change in displacement. We'll sort of look at where this could be used, but keep in mind, when we talk about the change in displacement, we are specifically talking about where the object's position changes from where it's launched. So say if the object is launched originally here, and then it falls down to this point here, we don't actually care about where it was launched midair. We just want to know where the start point is compared to the end point. This is the change in displacement. Now, as I also said, keep in mind very clearly which direction that is. Is this dropping below the launch position negative to you, or is it positive? I tend to just say anything that's going down is negative, so that's how I see it. AY is the acceleration due to gravity, so that's always negative 9.8, again, assuming that the motion that you describe as down is negative. Next one we have, and I'll just rub some of this stuff out. The next we have is the displacement. So the displacement we have here, we'll just change it into delta y, and this is the overall equation that we have here. Okay, so there's that. Those are the three equations you need to know for projectile motion for the vertical component. All right, so let's have a look at some of these questions. We have a ball that is thrown directly upwards with a velocity of 45 kilometers per hour. If we ignore air resistance, determine its peak height, its time of flight, its velocity, and its velocity after these 2 points. So let's show for that. Okay, so let's do question A here. So the equation we'll be using is this one here. Okay, so this will be used for question A. I'll just mark that as question A. Okay, so there is that. So we have original velocity of 45 kilometers per hour. Let's convert that into meters per second. So originally it was going 12.5 meters per second upwards, and I'm going to say that up is positive. I also know that down for acceleration is negative 9.8. So it's kind of like a thing that you automatically know to begin with. So you can always put that in. Okay. So if I substitute it into my equation, so I want to know what, so if the object reaches peak height, remember, the final velocity is always equal to 0. So we have 0 equals to positive 12.5 square plus 2, so times negative 9.8, and then delta y. Okay, and eventually what will happen, we will get a value. If you rearrange it, we'll find that delta y is equal to 7.97 meters roughly. Okay, I get a positive value, which means the peak height is above the launch position, which should make sense. Your peak height can't be below your launch position anyways. Okay, it's time of flight, so I'll write this down here. So the time of flight, if you look at all the information that we have, we know that when the object reaches, so when it goes from projectile and hits the final point, its final velocity is going to equal to 0. We already know what the initial velocity is. Okay, so final velocity, initial velocity, we know what acceleration is, we just need to find time. So we're going to use the first equation here to answer question B. So if I substitute all the values that I know that final velocity is 0. I know that the initial velocity was plus 12.5. I know the acceleration was this value here, and then t. So I can just rearrange my equation around, and what I'll find is it's equals to negative 12.5 divided by negative 9.8. So we get approximate number of about 1.28 seconds. Now remember, this point is 0, but we also have another point here where the velocity is also 0. So what we actually found originally here with 1.28 is actually the time it takes to reach peak height, not trip time. What do? Just make sure the ball is thrown directly upwards, so it will reach the same height at which it was launched, where it falls. So just times that by 2, and that will be trip time, which is roughly 2.56 seconds. That's the total time for the entire trip. Okay, and then I'm going to show you one where it's velocity after 0.5 seconds, and then you can sort of work out what the velocity is for the 1.5 second scenario is there. The equation we're going to use is this one here. Okay, the final velocity we want to know, the initial velocity you already know, 12.5, and then we know the acceleration, and then we know the time. So the overall acceleration is 7.6 meters per second, positive, meaning by at 0.5 seconds our object was still moving upwards. Okay, so there's that. You can check these calculations as well if you want to know a better understanding of all the working out there. Right, so now we move towards projectile motion in the horizontal component. Now this one is relatively more straightforward. Because there's no force being experienced by an object going in the horizontal component, as we assume there's no air resistance, there won't be an acceleration applied onto our object. So A is 0. It will travel at a constant speed, meaning by the final and initial velocities will be the same, and then all assumptions of air resistance is ignored as we talked about before. So you can see how that works there. So using the same 3 equations, let's just convert that into our analysis of projectile motion. So with this equation that we have here, given that we're not going to consider acceleration, all we're left with is this equation here. So ux equals to vx. Should be the other way around, but doesn't matter. It is what it is. What I would also highlight to you is that these equations, these projectile motion equations, aren't given to you on the data sheet. They do give you the kinematics equations, but they don't give you the projectile motion ones. So you do need to know by heart how to change the kinematics equations into the projectile motion ones. In the second equation we have, again, acceleration is not considered, so we actually just end up rewriting. So as you can see with this equation here, we don't have acceleration again, so we can actually just rewrite the equation like so, which essentially means the same thing as what we wrote up there as well. So nothing has really changed in that part there. And then our last one is the displacement in the horizontal component. Usually we call it the x displacement, sometimes we call it the range. And if we get rid of the acceleration, it looks a bit like this. So the change in velocity, change in displacement in the x component is given by this formula there. Okay, so if we look at this, these sets of questions here, we have an air gun that's fired horizontal target that is 81 meters away, and the bullet takes that amount of time to reach to strike. So obviously the best thing to do is always write down your components of what you have. Let's say this direction moving forwards, it doesn't really state, but let's just say that motion towards the right is the positive direction. So that's our formulas there. So if we substitute this formula in, we can always substitute the values in straight away. Ux is going to equal around 231 meters per second. And it's going in that direction, assuming that's what we assumed it to be originally. And then question 3, it says the gun was fired into the distance, direction ensures it takes 0.5 seconds to fall. Stop, what was the overall range? So continuing on from this question that we had up here, okay? So the displacement, like so, the speed we had was 231, times that by our specific time here, so 0.5. So it would have traveled around 115.5 meters, or if you would like to make it into 3 sig figs, 116 meters overall. Okay, so you can see the one-dimensional horizontal motion isn't too hard to do, and the y component in itself is not that bad either. It's when you combine those two together that makes it a little bit more challenging. And you can see these ones here. Okay, so just to get sort of an idea of where and how to analyze projectile motion, the first thing is understanding how to analyze the initial motion. All the scenarios we've talked about just then was nicely put into horizontal and vertical components. Most projectile questions, probably all projectile questions, never tell you the horizontal and vertical speeds just by itself. You have to work out based on an angle or some other arbitrary information that you need to work out and solve. So let's say most projectiles fired at a particular angle theta. We do know, and they will tell you most of the time, the initial velocity. Maybe it'll tell you the horizontal and then work out the vertical, something like that. So imagine you know what the resultant velocity is, you know what the angle is. Then by that, you can make the assumption that the resultant velocity can be broken apart into its perpendicular components. If those words sound familiar to you, that's because that's exactly what you did in Module 1 and Module 2. If those words do not sound familiar to you, then you probably should have studied a bit more. Okay, so just to get you into the idea of how to break these components apart, remember your trigonometry rules: sine theta, cos theta, and tan theta. Okay, so if you want to find, let's say, the y component, you would obviously use sine theta, because our y component, if we're looking at it here, the resultant is the hypotenuse, the the horizontal component is the adjacent side, and then the vertical component is our opposite side. So these are all the kind of trig rules that we can remember. If we convert it and rearrange where the subject matter or the desired component is the subject, we get this. So the vertical component is equal to the resultant times sine theta. The horizontal component is equal to the resultant times cos theta. Another thing that you can work out is also the resultant angle of the solution. So if I want to find, let's say I found the final velocity. So if I found the final x and y velocities, you can find the resultant velocity of the projectile. Okay, there might be questions where they do ask that. Maybe they'll just ask the final velocities of the horizontal or the y. Who knows? That's why you need to be familiar with these. If you want to find the final angle of the projectile's motion, then you can see you can work out based using tan theta. Okay, because you have the x and y component. If you have the resultant component, then maybe you'll use sine or you might use cos. But that's how you can actually work out the final and the initial velocities of a projectile. Okay. All right, what I'd like you to try and do is solve for these questions on projectile motion. So we have Finn was fired from a cannon at a velocity of 880 meters per second. If the elevation was 30 degrees above the horizontal, what's the vertical and horizontal components? So this is just practicing your ability to solve for the vector components. Okay, so if I want the vertical component, it's simply using the resultant velocity. Okay, and timesing that by sine 30. That'll give us a value of 440 meters per second. If we're looking at the horizontal component, which is ux, that is 880 cos 30 equals to 762 meters per second. Okay, so there's that. A cannon is fired at a velocity of that, and then we have a angle. So again, and I'll just do this quickly. This is your working out here. And the horizontal component is that. Okay, if we want to work out the final velocity of this projectile's motion, we have to, well, we actually know that the horizontal component will have the same velocity at the end, so Vx is going to be the same, but Vy will be different. So Vy, we have Uy plus AT. We know what T is, we know what A is, so let's use that. Again, positive direction is going up, so plus 200 plus negative 9.8 times 30 seconds. That gives us an answer of negative 94 meters per second. So we can actually work out what the final resultant velocity would be. So our final resultant velocity is going to be 94 squared times, let's say that was 346 squared, to give us a value of roughly 359 meters per second. Now remember, this is a two-dimensional motion, so you also need to work out the angle. Now if I work out the angle, so I know that the object is coming down like this at 94 meters per second. Just get rid of this diagram here. And we are traveling in this direction at 346 meters per second. Then the resultant vector looks a bit like this. So the angle of approach is this angle here. If you look at that angle there, we have our adjacent side, we have our opposite side, we're using tan theta. So theta equals tan inverse 94 over 346 equals 15.2 degrees. Now, this is going to be below as you can see, this is going to be below where we originally launched it. So we're going to call it below the horizontal. Okay, so we're saying we've passed where it should be. The reason why we know that is because the velocity is a negative value there, like so. So it is falling, and it's fallen below in this kind of angle here. So it's falling at an angle of 15.2 degrees below the horizontal there. Okay, so that's how you do that. Okay, and so that concludes our lesson on projectile motion. Hopefully you get a bit more comfortable with the actual equations we use, and obviously you understand how to break the resultant vector components and into the y and x components. If you had any issues, try and watch the video again. If you want to try and apply some of that knowledge, try one of the exam question videos and see how you go with that. Until next time, see you.